right, so this lab, this was a silver reflection lab, and I guess what was interesting about this is it was very similar to the Fresnel coefficients lab, except we're using silver. Now, we know that silver has an index of refraction that's complex, about zero point 0.5 plus 4.3 I. But it's essentially the same setup. Whereas with the Fresnel, so the only thing that's different. So here's we got the laser, bouncing off one mirror to the second mirror, and now it's the light that's being transmitted off of this mirror that is the light that's going into that we're saying is the incoming light, and then the light that's reflected off is the reflected, obviously. So none of this actually matters in terms of our calculations. Again, so what's interesting here is that is that what changes though is obviously our imaginary number. And one thing I got to look up, and I'm not quite sure, is how do I work with that? I mean, this equation seems to make sense, right? Where is it? You had it right here. We know that the Fresnel coefficients is dealing with reflected light. Excuse me, it's the so RP and RS. We need, as you write here, we need Fresnel equations which require a transmitted angle, but even though we cannot measure those, but we get those here. It's through, here we are. It's through the measurement. It's using Snell's law. Basically, we know that. Here we are. That angle out equals arc sine n1 over n2 sine theta n. But how does that change when we're using imaginary numbers? Because what's going to happen is that this value, because our ratio, our n1 is 1, but our n2 is imaginary, that ratio is going to be imaginary, and that means that to make this real, we need an imaginary sign, and that's what we're kind of confused about. So that's one thing to fix, is how does that work? And then, okay, so we do that, and then the other thing that was really different was in the previous lab, what we did was we just measured the reflected light, reflected S and reflected P. But what that didn't take into account, though, was that the apparatus, and let me go back to that page here, is super sensitive. Oh, wrong page. That one right there, you would have seen that about 20 minutes ago if you watched my previous video. This is a really sensitive apparatus, and I mean, you knock the lasers a little bit, or you do something. This is very sensitive, so that the amount of light that actually goes in that we can measure changes. So that's why we decided to to also measure in and not just out. And as you can see from our data, let's go there. Oops, see, wrong spreadsheet. There we go. Clearly, there's a big variance here. I mean, I don't know why. I don't know if something got bumped or something got changed, but accordingly, the R value there also went up. So like even though we've got some proportionality going on here, but that leads to another problem, and that is that okay, these Fresnel coefficients, they're good and fine, they don't change, but what does change is how do we interpret our data. And that is it simply just because here what you're doing is you're subtracting out the P, the reflected P minus the noise, which we certainly collected. But we also then have the the P in and the S in, and that I don't know if it's a subtraction problem or if that's just or if there's some division needs to happen. So if I take the ratio, or if I just take some sort of, or if I just subtract it out, that is certainly needed and of interest. So anyway, so I guess to go into this apparatus here, as I'm trying to wrap this thing up, what we have is is that so what we did then is that we had a we right here we had a to measure the incoming light. We just took the detector, we measured that, and then it gave us and then it was hooked up to a power meter, and it told us how much the intensity of that light, or how many in terms of volts, which is proportional to intensity. And then what happened was, and then we did the same thing over here with the amount reflected for the intensity. I guess the interesting thing is that it was at this point where we polarized the light. I know that one of the problems we had with one of our labs is that we threw the polarizer over here, so then which was too soon. Polarize the light here, both S and P, to get as accurate readings as possible. We did S and P reading here, and then we did S and P reading there, very quickly, because things just change so fast with that apparatus. So anyway, so the help I need is analyzing crazy data, and what do I do about the imaginary number part, so that I don't get an imaginary angle, because that's probably not going to work. And then also, what do I do about that incoming light, and how do I use that? How do I analyze that? And once I can do that, then I can propagate error and then give you a full lab report.